ASAP includes an integrated tolerancing capability that allows you to tolerance designs in both the builder as well as within the scripting environment. We can use tolerance analysis to model the effects of errors in manufacturing of mechanical parts or variabilities in optical components such as the index of refraction or dispersion of optical materials. We can also use the tolerancing capability to perform what-if type analysis on our systems. What happens if there's a change? What happens if our angles of incidence vary? What happens if our coating thicknesses vary, etc.? We'll start by looking at a case in the builder environment. Let me open up a file. And in this particular case, let's run the file and then we'll talk about what we're looking at. What we basically have is a surface made of BK7. And on that surface is a quarter wavelength of magnesium fluoride, a quarter wavelength defined at my system wavelength of 550 nanometers. Currently, the light is incident upon that surface at an angle of about 45 degrees, defined by this command here. And obviously, how much energy passes through that surface is a function of, among other things, the angle of incidence, the coating thickness, etc. If we look a little further down in our script, what I'm doing is looking at the two surfaces defined on either side of our interface. These are my two detectors. This is what I'm calling detector 1, and this is detector 2. And I'm using these surfaces to determine what the efficiency of this particular interface is. If I look back at my builder file here, I have a stats command considering only detector 1, and I'm grabbing some information from that, which includes the information about the total transmission through that surface. I can also get that same information about the reflected energy that's seen on detector number 2. If I look in my command output window, and I'm going to undock this so we can get a better view of it, here's the stats command first applied to detector 1, and what we can see is that in the current configuration, about 90% of the energy is transmitted and about 10% of the energy is reflected. What we're going to look at in this analysis to show you how the tolerancing works is to see how that transmission is affected as you change the angle of incidence. Now, I'm going to make a couple of modifications to my file first. I don't want to spend time constantly redrawing the window every time we change the angle of incidence, although in all honesty there are times when that would be useful. So right now I'm just going to use the option within the builder and simply comment out these lines. And now I'm going to add another trace command, this time without the plot option. So we'll define the system, we'll do the ray trace, and then we'll perform the analysis. And what I need to do to perform the tolerance analysis is first tell ASAP what parameters to perturb, and the other is to tell ASAP what my particular merit function is. And in this case, what I'm interested in is simply what's the transmission through the surface, and what I'm going to vary is the angle of incidence of the light on the surface. And here's how I do that. I'm going to simply vary the x term in the direction cosine definition. The y term will automatically be calculated so that the square root of the sum of the squares is equal to 1. But after selecting this cell in my spreadsheet, I simply use my right mouse button and I get the option to select a tolerance range. And what I'm going to allow is, let's assume we'll take a uniform distribution, and obviously the value of the direction cosine can't exceed 1, so it can't increase by more than, say, 0.29, approximately. And it can go down as low as 0, so I can go down to a minus 0.7. So this will allow ASAP within the tolerancing editor to select z direction cosines anywhere from approximately 0.007 out to 0.993. Close enough to the full range. And now I'll just click on OK. To tell ASAP to perform the tolerance analysis, I just need to click this button on my Builder toolbar. This is my tolerance toggle. And if I do that, what I can select is a number of iterations. and let's select 15 in this instance. I can also define my figure of merit, and in this particular case, I've already run this file, and the merit function that I'm using, or the figure of merit, TRAN, is already listed. I can use as a figure of merit absolutely anything that I can calculate within ASAP, either directly or via any mathematical manipulation I choose to add to it. But again, for our demonstration purposes, we're just going to see how the transmission through a quarter wavelength of magnesium fluoride on BK7 is affected by the angle of incidence. So all I have to do is click on OK, and ASAP will perform the analysis. And now we see the results of the calculation. And as you can see, our transmission varied from about 33% up to about 93%, again, depending upon our angle of incidence.